Okay, so we're going to talk a little bit about how to apply a magnetic field to a moving partner. Moving partner. Moving particle. Um, I am at home right now, and my cat Sydney is on my lap, so I hope, and she's taking up a lot of space. It's making it a little hard to draw, but I hope I can explain things to you guys. So let's say we have a particle moving through a magnetic field. The particle has a velocity v. I'm going to give the particle a charge q and a mass m. And I'm going to, for the moment, I'm going to arbitrarily say that the particle is already moving at right angles to the field. This will make it sort of easier initially to explain what's going on, and then we can sort of look at the general case of when the particle is not moving at right angles to the field. Okay, so the particle is moving at right angles to the field. This is the field here, this vector b, and I'm drawing it going into the page. So, and there's a reason why I'm drawing it going into the page. That will become obvious in a moment, rather than coming out of the page. Okay, so to do this little problem here, I'm going to set up a coordinate system. Actually, let me set it up a little more like this, where this is x, this is y, and then for a right-handed coordinate system, you hold up your right hand, you'll see that z has to come out of the page at us. So this is the z-axis here coming out at us, even though it's not on the origin. You get the idea. I'm just showing the direction of z, but the actual z-axis, it doesn't matter. Okay, so let's express our quantities here in sort of in IJK notation, as we're used to. So the magnetic field B, well, it's got a magnitude of B, right? And it's going into the page or into the screen. So since Z comes out of the screen at us, the direction of B is negative k hat. So the vector form of the magnetic field B is negative b k hat. Okay. The velocity, we're just going in the x hat direction, right? So the velocity is your speed, which is the scalar v, times I hat, because you're going to the right. If you're going to the right, that's your velocity. You are going into the page, that's your magnetic field. And so now, what's the force acting on this particle? The force is, well, we just take our usual equation for magnetic field force, and that is QV cross B, which equals QV, and then, wow, okay, so QV I hat crossed with negative, actually, let me make a more space here, crossed with negative B K hat, okay? And so, of course, this just means we take, we take the scalars together, and so this is going to equal Q, V, B, and then what's I hat times I hat crossed with negative K hat. So, and I swear to you, this is actually the way I do it. Here's my I, damn it, there we go. I, J, sorry, I forget you heard me say that. I, J, K, and then I, J. So I'm going I cross K, so I'm going to the left, which means I'm going to J, and so it's negative, and then I've also got the negative here. So I've got one negative because I'm going backwards in the list, and I've got one negative from here. So the force is going to be equal to QVB hat. And so the force, the direction of the force, is on the particle is up. Okay? So what we have here now is we have a force perpendicular to the velocity. That's perpendicular to the magnetic field. So I think you guys sort of see where this is going. What's the let's look at whether the speed of the particle is going to change here. So first let's look at the acceleration. The acceleration of the particle then is going to be the force divided by the mass, right? So this is just F equals ma, rearranged slightly. And so this is your force here. So the acceleration is going to be QVB over, sorry, there's Q, over m times j hat. By the way, I'm assuming the charge in the particle is positive. If it's negative, then this all gets reversed, but it still works out. So the acceleration is QVB over m times j hat. So it's accelerating upwards as well, of course. We can draw that with a acceleration arrow if we like, an acceleration vector. Okay, so it's accelerating at right angles to its velocity. I think we can sort of guess what kind of situation this is. This is uniform circular motion, right? this is what happens in uniform circular motion. You have an acceleration at right angles to your velocity. And what's going to happen is it's going to accelerate upwards, and then it's going to turn upwards, but it's going to keep accelerating at a right angle to its velocity, because at some later time it might be here, it might be going this way, but then you'll still have the magnetic field the magnetic field going into the page. It's still going to want to go at right angles to the velocity of the magnetic field. So if your velocity is like this, then your force and your acceleration will be like this, right? So you are always going to have an acceleration perpendicular to your velocity, and that is basically what you have in uniform. Well, exactly what you have in uniform circular motion. At any point, you're going to have a perpendicular acceleration. Yeah, Sydney, it's not making it easy when you sit on my lap like that and block half the screen. Okay, I apologize for Sydney. All right. Yeah. Oh, now put your paw on the touchpad. That helps too. Okay. Don't bite. All right. Anyway, so this particle is going to accelerate into a circle, and so we can find the radius of the circle, because that's just we can find all sorts of things about the circle, right? So we can find the radius of the circle by taking our good old friend A equals b squared over r, right? And so we take our acceleration was qvb over m, so qvb over m, and then we just we cancel some stuff there, and let's see, we can cancel. This would be okay. Now she's settling down again, thankfully. All right, we can cancel a v, and then we can get. Let's see, r equals m. Oh, it's going to be m. Mv over qb. Fantastic. Okay, so that's the radius of our circle, the circle that it makes. So this is for a particle traveling in circles in a magnetic field. R equals mv over qb. I'm going to write that up there. And then let's see, where else do we want to go with this? We can find, let's find the period of the rotation. So period, you'll recall, is the distance it takes to go all the way around, which is 2 pi r, and then it's divided by the speed, which is v. So now we can take this and plug in the r we found before, and find that the period is going to be 2 pi times mv over v times q times b. Okay. Well, and then you can cancel another pair of v's there, and find that the period of a particle moving in a magnetic field in a circle is going to be 2 pi m over qb. And so that's that's kind of interesting, because what you can see here, and I'm going to just put a box around this, not because you need to memorize it. You should be able to drive this again. You should understand this well enough to be able to drive it. And if you don't, then watch the video again, try it yourself, practice it. I'm putting a box around it just because it's kind of interesting. The period of this particle traveling in a circle in a magnetic field is proportional to its mass, inversely proportional to its charge, and inversely proportional to the strength of the magnetic field. But you'll notice that it does not depend on the radius of the circle, or on the speed. Any particle of any given size and charge in a given magnetic field is going to make circles with the same period, no matter how big those circles are. So what this means is you can have a particle, here, and say your magnetic field goes like this, and your particle can go in little circles or big circles, but they will all have the same period. Same period for all those circles. And this gets used actually in what's called a cyclotron, which is a device that's used to accelerate electrons up to some high speed and then spit them out. The cyclotron will basically have like two halves, so something like this, well, and then it's crappy, of course, and then one like this. And what happens is they have an alternating electric field that goes left or right. So the magnetic field always goes down through this part of the picture. And they have an alternating electric field that either goes left or right. So left or right for the electric field. And then the magnetic field, which I've done in orange, is always going down or up. And so the magnetic field ensures that you always go in the same period circle, no matter how big the circle is for the electron. And so you can just alternate the electric field at some set frequency. And what will happen is this electron will start in here and will spiral outward at some constant frequency, getting bigger and bigger as the electric field alternately sort of pushes it to this side or to this side, and it'll sort of pump it up basically until eventually you have a little hole in the side of the cyclotron, or like you have something like this, and the electron spins around bigger and bigger circles until it comes out. It goes boom like that. And so it's basically the cyclotron is a device for just shooting electrons, accelerating them up to some high speed and shooting them out. It's called a cyclotron. Well, cyclo comes from going in a circle, and tron, back in the 60s, people thought tron was the cool suffix. So everything under the sun was named as something tron. So instead of calling this like a video, we'd call it a visuotron or something. Or instead of calling these vectors, we call them vectortrons. Instead of calling this letter A, we call it atron or something like that. Well, not really, but so anyway, that's one application. I'm going to show you another couple of things you can do with magnetic fields and charged particles in other videos.